Welcome viewers to the second segment of the second lecture for the online series of lectures for the course of General Relativity. So in this segment we'll study another interesting example of a smooth manifold called two-sphere, which we denote by S2. Okay. So before I proceed, I need a picture for clear visualization of this two-dimensional sphere. Okay, let me try to do it here. I'm trying to draw a soccer ball. So this is the equator, one of the equators, which separates the upper hemisphere from the lower hemisphere, and there is one called left hemisphere, and there is one called the right hemisphere, and this is the separating, great circle. Okay, so this is what we call S2. Now the axis, this is what we call X2. Okay. And this is X3. This is X1. Now let us try to use a different color for the left hemisphere to differentiate it from the upper hemisphere. I'm drawing the left hemisphere with shaded blue color. This is the left hemisphere. For which X2 is negative. Okay. Strictly negative. And now I need the upper hemisphere that I'm going to shape by white color. Red color. This is the upper hemisphere. So the upper hemisphere is U3 plus, and the left hemisphere is UT minus. Okay, so let me explain these notations. We are going to denote by U1 plus the following set. I don't need it anymore. U1 plus is, this is R3, is all order triple belonging to S2, the soccer ball centered at the origin. Okay, so S2 is the two-sphere unit two-sphere of radius 1, unit two-sphere centered at 0, 0 of R3. Okay, so it's a collection of all order triples and S2 such that X1 is strictly positive. Okay. Similarly, you have U1 minus, which is the collection of all ordered triples belonging to the soccer balls, unit soccer balls, such that x1 is strictly negative. Similarly, one has u2 plus is the collection of all ordered triples x1, x2, x3 in S2 such that x2 is strictly positive, and then you have u2 minus, which is the collection of all ordered triples x1, x2, x3 in S2 such that x2 is strictly negative, and then we have u3 plus, which is the collection of all ordered triples in the 2 sphere such that x3 is strictly positive, and finally one has u3 minus, which is the set of all ordered triples in the 2 sphere such that x3 is strictly negative. One can immediately see that the union of all these open sets in R3 is precisely S2. Okay. Although if we take the union of u1 plus and u1 minus, it's the whole S2 minus a great circle that separates these two open sets. Okay. And similarly for other open sets that we are considering. Okay, so now we need some homeomorphisms, which are like projection maps that we considered for the circle example. For example, we consider phi 1 plus to be the map from u1 plus to R2. Okay, something like u1 plus is the hemisphere for which x1 is strictly positive, and then we are going to project it onto the x2, x3 plane. Okay, you take all the points on the hemisphere are projected onto the x2, x3 plane, and that is R2 in the following way. We take an element of u1 plus, which is x1, x2, x3 say, and it's projected onto just x2, x3, a pair. Okay, so you disregard the first coordinate. So this is how phi 1 plus acts on u1 plus. Similarly, one considers phi 1 minus, which is the map from u1 minus, which is of course a subset, an open subset of S2 from R2 by the following action: phi 1 minus acting on x1, x2, x3, where this triple is from u1 minus, and that is projected onto the pair x2, x3. Just disregard the first coordinate. Okay, good. Similarly, one can define phi 2 plus minus using the following action by disregarding the second coordinate, and phi 3 plus minus acting on x1, x2, x3 by disregarding the last coordinate or the third coordinate. Okay, so this is how you define these 6 maps. These 6 maps: phi 1 plus minus, phi 2 plus minus, and phi 3 plus minus. Now, the claim is that u1 plus, phi 1 plus, u2 plus, u2 plus, phi 2 plus, u3 plus, phi 3 plus, u1 minus, phi 1 minus, u2 minus, phi 2 minus, and finally u3 minus comma phi 3 minus. So the collection, the set of all these 6 pairs is C infinity at last. C infinity at last is a C infinity at last for S2. Okay, so where we already defined this open sets U1 plus, U2 plus, U3 plus, U1 minus, U2 minus, U3 minus, and we also defined the corresponding homeomorphisms. One can easily see that these are also homeomorphisms from the underlying open sets of S2 to the corresponding Euclidean spaces, Euclidean space R2. Okay, and so these open sets U1 plus minus, U2 plus minus, and U3 plus minus cover S2, meaning that the union of all these open sets is equal to S2. Now one needs to check that the underlying homeomorphism, the underlying charts are pairwise compatible with each other. Let's see. Let's have a closer look at that. So okay, so let's try to construct this guy. Phi 1 plus composed with phi 2 minus inverse, okay, which is supposed to act on phi 2 minus of u1 plus intersected with u2 minus to phi 1 plus of u1 plus intersected with u2 minus. Okay, so if you take this map, phi 1 plus composed with phi 2 minus inverse, and take an arbitrary element from this set of R2, which is of course x1 comma x3, because if you choose an arbitrary element, right, x1 comma x2 comma x3 in u1 plus intersected with u2 minus, okay, and then the action of phi 2 minus on x1 comma x2 comma x3 from the definition of phi 2 is going to be simply x1 comma x3 by deleting the second coordinate or by disregarding the second coordinate according to the definition of phi 2 minus, and therefore this phi 2 minus inverse is supposed to act on this pair, this outer pair x1 comma x3. Okay, good. Now this will produce phi 1 plus and then phi 2 minus, the inverse of phi 2 minus is supposed to take it back here, okay, but so x1 comma x3, so this is going to be the first coordinate, x3 is going to be the last coordinate, and the second coordinate of this triple, order triple, is going to be a negative quantity because it's going to be in u2 minus, right? So that's why, but according to the definition of circle, according to the definition of a two-sphere, the square of the three coordinates should produce the sum of the square of these three coordinates. should be equal to 1, right? Because the equation of sphere, of a two-sphere, is this, right? So the only way we can have it by fixing x1 and x3 is minus square root of 1 minus x1 square minus x3 square. That's going to be my second coordinate, and presence of minus sign means that we will be in u2 minus. Good. So now, according to the definition of phi1 plus, I have to disregard the first coordinate. So that will project me to this pair negative square root of 1 minus x1 square minus x3 squared comma x3. Okay. Good. Therefore, we just found out that phi1 plus composed with the inverse of phi2 minus acting on x1 comma x3 will yield this pair. Negative square root of 1 minus x1 square minus x3 squared comma x3. Okay, so now observe that nowhere on this open set u1 plus intersected with u2 minus is x1 square plus x3 squared is equal to 1, meaning that, well, what is x1 square plus x3 square is equal to 1? That's precisely the unit circle of, unit circle on the x2, x3 plane centered at the origin. Okay, so this unit circle centered at the origin on the x2, x3 plane. But that's not included in this open set, right? You cannot have this guy, this circle, in this open set. And that is the reason this map is C infinity. Why? Because if you see that, because when you try to differentiate it with respect to x1 or x3, you'll have this square root of this expression appearing in the denominator, and if x1 square plus x3 square is equal to 1, the expression is going to blow on the circle. But since the circle is not present in this open set, this is C infinity. This expression is going to be C infinity, infinitely many times differentiable. So this way we immediately see that this transition map is going to be a C infinity map on this open set. From this open set to this open set. Okay, good. Which means that this guy is indeed a diffeomorphism, meaning that it's a bijective differentiable map with the differentiable inverse. Okay. Good. This way we check that all the charts involved in the atlas are pairwise compatible, and they indeed form an atlas for the underlying differentiable manifold. So we just studied the atlas structure of the underlying differentiable manifold. Not going into the detail of the topological structure, like it's being it being second countable, it being Hausdorff and all these things. These are discussed in detail in the course of differential geometry that we did in the last semester. Okay, good. Now we move to the discussion on smooth maps on manifold. Now that we have a concrete definition of a smooth manifold, we'll try to study smooth maps on a manifold. smooth maps on a manifold. Definition. Let M be a smooth manifold of dimension n, a function f from M to the real line R, bold-faced R, is said to be C infinity, or smooth at a point P in N. Okay. If there is a chart U, phi containing P. By the containment, I mean that P is contained in this open set U, or which is one of the components of this pair U, phi, in that class of M. Okay. Such that, so if there is a chart containing P in the atlas of M, such that F composed with phi inverse from phi of U, which is, of course, so it's better to write it this way, Rn containing phi of U to R is C infinity at phi of P. The C infiniteness, or the smoothness of this map, this is a map from R to the N, a subset of R to the N to R, which means that we can study the smoothness of such a map using our knowledge of multivariable calculus that we studied in our first lecture. Okay, so this is precisely the reason we studied various aspects of multivariable calculus in the first lecture. Okay, so this is the definition of a smooth map on a manifold. Smooth, smooth function at a given point on the manifold. Real value smooth function. Okay, a real value smooth function on the manifold at a given point. Okay. Good. So let me draw a picture for this. So suppose that this is our manifold. So I'm going to avoid these corners. Make it a smooth manifold, and there is a point P here, and there is a chart containing this point P, meaning that there is an open set U containing P, and there is a diffeomorphism phi from this open set U of N to an open set phi of B, okay, and the image is nothing but phi of U contained in R to the N. This is going to be R to the N, okay, and F is a map, right, say from U to R, right? So F is a map from U to R, and phi inverse will take phi of U to phi of U to U, and then F will take U to R, so that the composed map is from phi of U to R. Okay, good. Now we need the notion of a tangent space. Okay, but iteratively speaking, tangent space are tangent, of course, to a point on the manifold. The ideal picture would be that of a point on a soccer ball, like this. Point on a soccer ball, and you place a plane on that point of the soccer ball such that it just touches that point, right? So this is a prototype of a tangent space that we denote by VP at the point P on the sphere S2. Okay. Sometimes we denote this tangent space by TPM. In this case, M is S2, the two-dimensional sphere, which we proved earlier to be a manifold. So TPM is going to be the tangent space to M at the point at P of M. Okay, so let me write it here. Tangent space TPM at P in M. Okay, it is spanned by the following set of vectors, tangent vectors to be more precise. D del by del x1 by P I mean that they are all based at the point P. Del over del x2 based at point P again, all the way up to del by del xn based at point P. There are n tangent vectors that span the space TPM, the tangent space to the point P of M. So why they are called tangent vectors? But you see that under a coordinate change or under change of basis that we study in linear algebra, if you have a vector space, then you go to a different coordinate system by changing the underlying basis. By a linear transformation, you change the basis of the underlying vector space, and that way a vector, when a vector is expressed in terms of these basis vectors under a coordinate transformation, the basis vectors also transform, and you can show that the transformation of the basis vectors under a general coordinate transformation is going to be the same as the way partial derivatives transform under change of coordinates. Okay, that's why these partial derivatives are, we express the basis tangent vectors with the help of these partial derivatives. That's roughly the answer, but the answer will be clearer to us when we study the tensor field and tensor. Okay, I'll come back to this notion later. But for the moment, see that this set of vectors, tangent vectors, span the underlying tangent space, which is considered as a plane to the manifold. Okay, there is a coordinate independent way of expressing a tangent space. We'll see now. So if you pick up an arbitrary tangent vector x, so always whenever we are talking about tangent vector, we'll restrict our notation to a given point, to the given point p, through which we are drawing the tangent plane or considering the tangent space. So if you are considering TPM, then whenever I'm writing a tangent vector, I should write it like this: x restricted to p, or x at p. Okay, so this is an element of this vector space. Okay, TPM is a vector space that one can prove. Again, we are not going into the detail, the mathematical detail of the geometric detail of these things, which are studied in detail in the course of differential geometry. But of course, x restricted to p is going to be a vector of this vector space, and in other words, if it's a vector, it can be expressed as a linear combination of the basis vectors. So we can write this guy as a linear combination where these guys are numbers, right? And these are vectors, del x I at p. Okay. So a general tangent vector, this is the expression of a general tangent vector. Written as a linear combination of the basis vectors. So note, an important thing here is that these vectors are maps from C infinity f comma r to r. So it means that the real valued functions on n. Okay. So the elements in this vector space is a function. Okay. So whenever you have a vector, a tangent vector here, it will act on a function from this space, and the resulting thing would be a number, right? So let us plug in this expression here, so that we have sum over I xip, which is of course a number, del over del xi restricted to p acting on f. Okay, and this is nothing but sum over I xi of p del f by del xi evaluated at p. So ideally this is going to be a number, right? Because this is a number multiplied with another number, because del f by del xi is a function, and that function evaluated at the point p is going to be a number. So two numbers multiplied with each other gives another number. Okay. So the right side is a number, and it is supposed to be a number according to the definition. Good. So now we need a well-defined notion of this guy, right? Let me erase this part. So we need a well-defined notion of del over del xi restricted to p acting on f, where f is an element of this space, right? In other words, f is a real valued function, real valued smooth function on M. Okay, so this is defined as evaluated at, well, psi of p. Okay, where p belongs, so p is contained in the following chart, where u psi, okay, p is contained in this chart, meaning that p is contained in this open set, and u comma psi is a given chart containing p. So okay, so f comma psi inverse is of course a map from psi of u to what? R, right? Well, to be more precise, this is going to be a function on u containing p. U is an open set containing p, right? So in that way, f composed with psi inverse is going to be a function from psi of u to r, right? Where psi of u is an open set in R to the n. Okay, good. So this way, this is going to be a number. So we're being a bit sloppy here in the sense that we have taken del by del xi restricted at p, these objects are considered both to be tangent vectors and at TPM and as basis vectors in R to the n. Okay, so here is the TPM and here is R to the n, right? So del over del xi restricted at p is considered basis vector here in TPM, and at the same time I'm saying that del over del xi at psi p is a tangent vector here. Okay, so this is a sloppiness. So in other words, this can be written down. So remember, we wrote like this, right? We defined like this: psi of p, f composed with psi inverse. Okay, so this we take a tangent vector in R to the n, and by the same del xi at p, we're denoting a tangent vector in the tangent space TPM. Okay, so this is what we are doing this. We are doing, we are abusing the notation in order to conform with our textbook written by Robert M. Walt. Okay, so this way, so we could have made it a little more precise the way we did in our differential geometry course by writing things in like del by del Ri when we are treating vectors in R to the n, and del by del xi when we are in the tangent space, but we are not doing it. We're not making any difference here, just to conform with the book by Walt. Okay, good. So to summarize, we write this stuff as del by del xi, okay, f composed with psi inverse, evaluated at psi of p, where p is contained in U and U comma psi is a chart of M. Okay, and F is a real valued smooth function on U. We are going to write the derivative, the partial derivative of the function F at the point P like this. Good. Now, smooth map between two manifolds. It's important for us to discuss what it means by a smooth map between two manifolds, but before that we'll take a break. And the last segment we'll discuss smooth map between two manifolds and how to express a tangent vector to a given point on a curve on a manifold. Okay. Thank you for attending the second segment.